Yeah. Thank you, everyone. Thank you for joining in. Today we have Professor Daniel, and he's going to talk about capacitively coupled excitation system. So, on behalf of IEEE PELS and IES Society Bangalore chapter, I welcome Professor Daniel. So, please go ahead, Prof. Please go ahead.
All right, thank you very much. So today, one of the things we're going to talk about is capacitive power transfer, and specifically for what are called wound field synchronous machines, or WFSMs. And I've structured this talk to be somewhat of a tutorial. So outline for today's talk, I'm going to give a little bit of background on the wound field synchronous machine and what it is and how it works, and then why capacitive power transfer is a good option for it. And then we'll move into how to use size of capacitive coupling and the power electronics and other aspects of it. So this project is actually a joint project with my colleague, Professor Ian Brown at the Illinois Institute of Technology, and I'm at UW-Madison. Professor Brown is handling most of the machine design aspects, and I'm handling most of the wireless power transfer design aspects. These are my graduate students that have been working on this project with me over the last few years. Some are recent graduates. These are Jen-John Dye and Ryan Knippel and Skylar Hagen, and my current student working with me on this project is Marissa Tisler. All right. So within this, a wound field synchronous machine is a machine that has electromagnets rather than permanent magnets. As you can see here, the field coils of this machine serve as the magnets on the rotor, and this is in lieu of, say, an IPM or interior permanent magnet machine where you have permanent magnets on the rotor. So these machines are ubiquitous as generators. They're everywhere. They're not as common as motors. And so the salient pole configuration shown has some terminal characteristics that are similar to an IPM, in that there's field and reluctance components, but it's with electromagnets instead. And so this has the potential to be lower cost and to have a direct handle on the magnets. So the advantages of the wound field machine are there's no permanent magnets, so there's no market volatility, no risk of demagnetization, potentially lower cost, and modern materials and techniques can yield almost PM level torque density. Direct field weakening. The field current in this machine is a third control handle as opposed to just ID and IQ. The inverter kVA rating of this machine, say in a traction application, can be reduced because there's no need to source D-axis current to buck PM flux and field weakening. And so the field current can be adjusted to maintain near unity power factor or greater power factor than a permanent magnet machine. And so you can therefore have a higher operating point for your inverter over more of the drive cycle. And the field can be turned off in a fault. The disadvantages for this machine are that there's added rotor mechanical complexity. So you have coils instead of permanent magnets. That's harder to do mechanically. They have to be wound, inserted. There's wire integrity, both at speed and wire insulation, and they must be cooled because you're generating I²R loss on the rotor. So you also have to supply power to the rotor, adding a power supply for the rotor, and so this is traditionally done with brushes and slip rings, and that's a reliability concern. But so brushless excitation approaches are more complicated, but we need to use them because they're just not going to be compatible with modern systems. You need to make it brushless. and the cost of the excitation system must be less than the magnets that you're replacing. So these are just some good references that I've found useful for Wanfield synchronous machines, and this is specifically for their use as traction drives. And so, if you're interested in using or reading up on this subject, I encourage you to look at some of these. All right, so this is more of a tutorial on capacitive power transfer, not necessarily a Wanfield synchronous machine pitch. So let's say you're a designer and you've reviewed the literature and your options, and you've made the decision to use a Wanfield synchronous machine. How will you excite the rotor field? And so a rule of thumb is that the stator ampere turns per pole are equal to the rotor ampere turns per pole at rated power for one of these machines. And so for a 100 kilowatt motor, it's typically 1 or 2% steady state or 3% peak for the field power requirement. So this is, 1 to 2 kilowatts, 3 kilowatts peak for the field. And then the percentage of the power of the overall machine that's required for the field typically drops as the power rating increases. So for instance, a megawatt scale machine would use a lower percentage. Excitation system options, there's a long and detailed history here, and there's an excellent review paper which I've put down at the bottom of this slide that goes all the way back to the 1920s and reviews the excitation systems for Wanfield synchronous machines, starting with brushes and slip rings and DC exciters, coming all the way up through modern day wireless power transfer, even capacitive power transfer. And so this is an excellent review paper, and so if you're interested in this topic, I highly encourage reading it.
Which lab are they in? Which lab is this from?
This is from the
England, Spain?
No, it's Norway. I'm trying to remember.
NTNU? NTNU?
Yes, I believe NTNU.
Okay. Yeah. Good. Okay. Good.
I know this is being recorded, so if it's wrong, if that's not the school, I apologize.
On record.
So, but anyway, it's a good paper, and check it out.
Good,
so without and with and without brushes. So these are some of the more common things that, so obviously on the left you have brushes and slip rings, and this goes back to the beginning of time of electric machines. You also have shaft-driven brushless exciters, which is another machine located on the shaft, which is then coupled to the main field winding. You then have rotating gapped high frequency transformers. So this is just a ferrite transformer that's had its primary and secondary windings free to rotate, but there's a small air gap in there that allows them to do that. And then lastly, a third harmonic injection to the rotor coils. And this is actually an invention of the recently deceased Professor Lippo, but we'll talk about that. So brushes and slip rings, they're simple, they're 150 years old, bidirectional power flow, and they're power dense, and they're cheap. The problem with them is that they mechanically wear out. Sliding contacts, friction, dust. They're not compatible with spray cooling. Modern electric machines use spray cooling on their windings, and then you can't get that spray coolant on the brushes and slip rings because that would disrupt their operation. And even the brushes and slip rings are even bad for the marketing folks.
Yeah.
So the brushless exciter, this is what's used in standby generator sets. It's contactless. It delivers power from the shaft. So it turns the torque and speed from the prime mover, say an engine and a genset, into the field power. It's another generator on the shaft powering the field of a larger generator. And so it's large for what it is, but that's acceptable in applications where you have a prime mover like an engine and a genset. but it's physically large and not suitable for a traction drive. Note that it does have a rotating diode bridge. Gap transformers, these are contactless, they're power dense, they're higher frequency, and so they're more compact, and then they're shaft speed and position independent. So the disadvantages with these are they're a specialized construction. You need a ferrite core and typically Litz wire. Ferrites at speed can be problematic, and so they may need banding for retainment. And then also a system such as this, you do need to consider cooling arrangements for it. And there's a rotating diode bridge, because if all brushless systems require a diode bridge because you're using AC to couple across the gap, you need a high frequency power electronic driver. And so the question here is, can you do all of that for low cost, and especially less cost than the magnets? And this is the Professor Lippo solution. And this one is, can you use the main traction inverter to inject third harmonic into the stator windings, and then you have a special winding embedded in the rotor to pick up on this third harmonic and then rectify it to feed the main field coil of the rotor. And you can see that in the cross section in that picture. So it's contactless, it utilizes the existing traction drive electronics, and so there's a certain amount of elegance that goes with this. But one of the problems is that it requires a specialized construction of the rotor with an auxiliary three-phase winding embedded alongside the DC field winding, and then pole structure of the machine is altered, and the field slot area is reduced for excitation. So this system impacts the main torque producing components, and so you have to optimize these together. You can't decouple them. And also it requires a rotating diode bridge, so you have to be very careful how you design this. So one of the things that's fascinating to me anyway, is all brushless options in wound field machines have a rotating rectifier, no matter what. And so only AC power can traverse a gap, and then you rectify it to field the DC magnets. And so the question I have is, can the rectifier board somehow become the coupling structure? And if so, that's innately low cost. So what we decided to do is, if you're going to have a circuit board that is the rotating rectifier, well, let's see if we can make that a coil as well. And so these are some circuit boards that we made, both square and round. The square was just to learn on the bench, and then we made round ones that could be mounted on a shaft. And we found that making a coreless option using only circuit boards, while it functioned, we had skin effect and proximity effect losses that were substantial, and eddy current losses in the surrounding bits of metal and end turns and things due to the fact that it's a coreless design. And so we decided to ultimately to abandon this in favor of capacitive power transfer for efficiency reasons. Excuse me.
So these are PCBs. Are these PCBs with the copper trace exposed, or these look a bit different? Yeah.
Yeah. So these the square ones were just copper clad that we machined ourselves away to make our spiral.
Got it.
And then the second one was a circular spiral, but we left the top tinned, so that way we could solder wires to different points on the spiral for experimentation.
Got it. Yeah, please continue.
Yeah, no worries. So the capacitive coupling approach we are looking at instead has the basic concept of, instead of two coils that are coupled, we have two capacitors that are coupled. When driven by a high frequency current source, you drive a displacement current through these capacitors to feed a load. And that's the basic concept you see on the left. And then the implementation of that is you have a rotary capacitor and then diodes and then the field winding, and that's on the right. And so if that's the case, you, instead of having these coils that had their ESR and their skin effect and the proximity effect and the eddy currents, what have you, we can make a coupling structure that would largely minimize those effects by having it be capacitive. And so some of my prior work in this space is pictured here. This is concentric sleeves on the left, made out of off-the-shelf journal bearings. These are just two sleeves that fit within each other, and then you can see the diode board and then these journal bearings here. And then on the right is a more advanced version, significantly more complicated, where we have a rotating capacitor that's many parallel discs that are very close together, 4/1000ths of an inch. And they, if you look closely, there's little grooves on the surface of the discs. And while it rotates, it works like a hard drive platter, and that the discs float on each other on a cushion of air that's trapped in those grooves. And so you can get very, very high coupling capacitances, relatively speaking, nanofarads. And so you can then do kilowatt power transfer in the hundreds of kilohertz. But both of these systems are mechanically complicated, and we want it to be simple. And so we need to what we need to do is use GaN to push into megahertz switching, and so we can just use picofarads of coupling capacitance and make a much simpler structure.
So this was made in-house?
These were made in-house by my students. So
Really good.
It took many hours in the machine shop.
Obviously,
Many hours in the machine shop. And so one of the things, so some of the original ones I made myself, and then my students improved upon them and made them even better through many hours of design and machine shop.
Got it. And when you used GaN, I don't know whether you'll talk about it, did you face any false turn-on issues when you used GaN?
Yes. So in the presentation, we can talk about that, but
yes.
The GaN's a little bit further ahead, and so so we'll get into the coupling structure here, and then we can get into the other aspects a little bit later. So what we decided to do was to make a circuit board that looks like the rotary configuration here, and where we have two concentric rings, two boards facing each other, and that looks like what you see on the right, which is a stator disc and a rotor disc, where the stator disc is simply facing the rotor disc, and you have these coupling capacitances. So, and then at the center, you can then place your rotating electronics at the center of the disc. And so you form capacitances between 1 and 2 and 3 and 4. And then on a machine, it looks something like this. So this is a wound field synchronous machine with the two discs installed on one side. And then these discs would then transfer power over to the rotor. So this is the rotor of the machine that we had available to experiment with. This is a 30 kilowatt continuous 55 kilowatt peak 4,000 RPM base speed machine. It requires 4 amps DC field current, and with a field resistance of 42 ohms, that comes out to about 675 watts of power needed to drive those coils on the rotor. So our system needs to be driven from a greater than 300 volt DC main traction inverter bus, and that needs to fit within the machine. So these are the rough dimensions of the machine: 6-inch OD rotor, 10-inch OD stator.
So the objective of Department of Energy proposal was this itself?
Yeah, so this was the specs of this machine were in this DOE award, and that machine was an outcome of that DOE award several years ago. So this was that DOE award was in my earlier work from, I want to say, 2015 to 2017 or 14 to 17, somewhere in there. So this is the machine that came out of that award, and we decided to use it for this experiment.
Good. Yes, please go ahead.
And then this board here, so the first step is we have to figure out, if we're going to make a circuit board, how do we size all these radii and dimensions? And we have inner area, outer area, a gap D between them and these radii. So how do we size our capacitance? And so obviously it kind of makes sense to put the electronics at the center, because the machine is going to be spinning at a high rate of speed, and so the G forces on the electronics will be minimized by minimizing the radius at which they are placed. Simply, V squared over R. And so in this case, we need to place them close to the shaft, so they'll be at the ID. And also the structural integrity of the circuit boards is going to be governed by the Young's modulus of FR4 material. And so we had to measure that, and that's reported in our 2019 EC. And if we go ahead and say, well, what do we want? And the double-sided circuit board is more attractive because you can get more capacitance without increasing the number of rotors you have. You have another stator, but you only have one rotor still. And so what we'll do is have a rotor board that is sandwiched between two stator boards. And so you get double the capacitance for that. So although this seems simple in terms of you have 4 electrodes, you actually get a lot of capacitances. So considering ground is the 0th, if you will, capacitance, this is a network of 10 capacitors between 4 electrodes and ground. But we only want 2 of the 10 capacitors. The other 8 are all parasitic, so we don't want them. And if they're in play, if we don't manage them, they'll result in extra loss. So, but let's first begin with the ones that we want, because those are actually ones you can model analytically. So if you align the areas for facing dimensions, you can, and if the area is such that the radii are much bigger than the gap, then the basic epsilon A over G equation applies. And so then what you do is you want the effective area of the outer ring and the inner ring to be the same. And then to do that though, because there is a gap, the same trick that you apply in sizing magnetic gaps analytically, where you add the dimension of the gap to the facing area, also applies to capacitors. And so in this case, we add and subtract the gap length G to the radii as necessary to account for the fringing. And that's area 1 and 2. The distance between the 2 rings, D, is set by just the difference of R3 and R2. And so you set these 2 areas equal to each other, and then you solve. So the constraints for solving that are the R4 the radius, outer radius, and R1 the inner radius, and then the spacing between the electrodes. And so you constrain those based off the dimensions of your machine and your shaft and where you're placing your electronics. And so ultimately the only unknowns are R2 and R3. And so then you then solve for your R2 and R3 based off that. So what about the other 8 capacitances? So we had to do a FEA to do that, but in hindsight of doing the FEA, we came up with the following design rules. And these are design rules that came out of the FEA analysis. So clearance distance D between R2 and R3 also about 10x. So in this case, about 8 millimeters. The main coupling surfaces are to be mirrored on both sides of the board, and so I'll get to that in a minute. And then we want to slot out the oh great, we want to slot out the area between these. So slotting the area out is this white gap here. And then don't run traces through the inner layers of the boards to avoid overlap. So when I was talking about mirroring, it's about, we want to maintain this gap here. And to maintain that gap, the boards cannot be warped. When you get a circuit board from a manufacturer, oftentimes it's warped, and I guarantee it'll be warped if you have copper on one side, no copper on the other, because you now have differences in thermal expansion. The copper will heat up and then expand, and then the FR4 will not, and you'll warp the board. So you need to have copper on both sides of the board in order to maintain it nice and flat and parallel. So that's design rule number 1. The other thing is if you have 2 copper traces on both sides of the board of equal potential, there's no field cutting through the FR4, and so therefore there's no dielectric loss in it. The next thing you need to do is, you see these slots cut in the discs between the inner area and the outer area? These were cut because if you leave the FR4 in there, you have a large displacement field because these traces and these traces are different potentials. And then the displacement field between them will generate dielectric losses in the FR4 material. By slotting that material out, you then minimize that loss and the cross-coupling capacitance between these traces. You have to leave these spokes, though, for mechanical purposes. I mean, obviously, because to keep it a disc, but you slot out as much as you can. The other thing is that you need to connect the outer ring to the electronics at the center. The problem is that, so naturally you think, I'll make a 4-layer board and I'll route the connection from this outer ring through a center layer of the board to the inner rectifier. You don't want to do that. And we found out the hard way because our board got really hot. But what happens is the displacement field is so large on the interior of the board that we had all of this displacement field here that caused additional loss. And so what we decided to do was to slot the inner effective area, or the area of the inner ring, to pass the electrode connection through the surface instead. And so that minimized the amount of displacement in the FR4 and lessened our loss. And so what the resulting rotor board looks like, so this is the board that spins. We have an outer area, an inner area, and then our rectifier electronics at the ID. And then we have two stator boards that go on either side of it, and that's these here. And so it's and so this is our rotating capacitor. So to measure what we have, you have to use what's called a partial capacitance method. Because if you measure at the terminals, which are 1 and 2 on the, 1 and 3 on the stator, and then 2 and 4 on the rotor, because these are the quote-unquote areas that are facing each other here. But you have all these other capacitances that exist in parasitics. And so you need to measure these. So you need to create a set of 10 equations with 10 unknowns to find all these capacitances. And so what you do is you can take, you can measure the capacitance of between ground and terminals 1, 2, 3, and 4 all shorted together. And then you can measure the capacitance of ground and terminal 1 shorted together, and then 2, 3, and 4 shorted together. And so it's just doing the nodal analysis of all the different combinations of terminals to then create the following matrix, where you have the different total capacitances from the terminal combinations, and then which terminals you've shorted together and left open is determined by this matrix, followed by the actual capacitances you're interested in, and then you're able to solve for these just using matrix analysis to get the actual capacitances or so-called partial capacitances of that system. And so once you do that, you can see that within our network we have, these are our coupling capacitances. Here's all of the other capacitances, that we didn't want. So analytical methods predicted that we used when we solved for our equal areas predicted 300 picofarads is what we would get. The measured values are 288 or 268. These are within 10% of measured, which is pretty good for an analytical method. The gap was slightly larger than we intended when we measured it, which is most of this difference. Excuse me. And C12 is greater than 334 due to the fact that the outer ring has a larger periphery, and so it has a slightly larger fringe field, and so that's why this capacitance is slightly larger than this one, but they're pretty close. All the parasitic values, by implementing the design rules I discussed, are all in order or 2 orders of magnitude larger than the capacitances that we want. And so we can largely ignore these for the analysis of our system. So this is before and after the design rules. No, this is a picture of using a thermal camera of when we routed a trace through the center in a 4-layer board. You can see the inner traces of that board are glowing in this picture. And so and you can see here in our original version of this board, we had on average 6.6 ohms, and then after we implemented our design rules, it dropped to 2.8 ohms of ESR. So that was a 58% reduction in ESR with the design rules.
Just one quick question. For the frequency plot, where do you have the input port and where do you take the response?
So what we did was we're measuring this in circuit. So it's in a resonant tank for power transfer, and so this circuit is more than just the boards. It's actually also the resonant tank inductor. So these capacitors, we formed a resonant tank with a tank inductor, and that we found that was the easiest method to figure out what the ESR of the system was to measure it at resonance.
Mm-hmm.
And so, but what's more accurate to state is before and after we implemented the design rules, the ESR of the resonant tank dropped. And we'll get to that tank circuit in a little bit.
Okay.
So the average coupling capacitance is 278 picofarads, which is right here. This is our terminals. And so we need to figure out, well, if we want to get power over here, how much current IAC can we pass through this capacitor before the electric field in this air gap breaks down? And if you do the analysis on that, the voltage across the capacitor divided by the gap is the field. And then in this case, if it's just simple circuit analysis of the impedance of the capacitor is 1 over omega c, and then the voltage across that is you multiply by the current going through it, Ohm's law, and then the gap. And so you find out that the amount of field or the amount of current that you can put through here is determined by the electric field breakdown of air, which is 3 kilovolts per millimeter, in relation to the current, the area, the permittivity of free space, and your operating frequency. And so transformers are governed from a saturation perspective of volts per hertz. So the flux is governed by volts per hertz. In a capacitive system, it's governed by amps per hertz, or in this case, amps per megahertz. And so one of the handles you have is the ability to have a current go through this and for a given amount of area, and then or current density relative to free space and frequency. So how does it show up graphically? So if I have 278 picofarads in a certain air gap, I can have, for 3 kilovolts per millimeter, the maximum current that I can put through, or the breakdown current rather, is going to be, using the equation at the bottom here, is going to be 4.2 amps roughly. And that's the peak value of a sine wave. That in RMS is going to be 3 amps, or 2.96 in this case. And this is where I would break down. If I want to derate my system to give myself some margin before, if I derate my system by 33%, in this case, I have 2 amps. And so the slope of these lines is the amps per megahertz rating. So what that would mean is at, say, at 1 megahertz, I can put a maximum or a peak value of 4 amps or so and through this capacitor before it breaks down. Peak, which translates to about 3 amps RMS, and if I safely derate it, it's about 2. So in this case, if I run my system at 2 megahertz, though, I can have double the amount of current. If I run it at 3, I can have triple the amount of current. And so the amps per megahertz rating tells you how much current you can put through a capacitor for a given frequency. Oops. Now, these capacitors, even at megahertz frequencies, still have a large amount of reactive impedance. And so we need to cancel that out. So if I want to push 4 amps through here for my 4 amp field winding, I need, unless I have tremendous amounts of voltage somewhere over here, which I don't, I have a few hundred volts from a DC bus, then I need to use resonance to cancel out this reactive impedance of the capacitor. And so I add inductors in series. In this case, at 4 amps, it's going to be around 4.4 kVARs of reactive impedance that I need to cancel in the capacitor with an inductor. And so the design of these inductors is non-trivial. So I need to have a multi-kVAR inductor at megahertz frequencies. And so most wireless power transfer folk use air core inductors, and that's, while it's convenient, it's not really practical, and it certainly ignores a lot of EMI, EMC issues and the like. So we want to use a cord inductor that can be multiple kVAR and megahertz. So we actually use a design that was that came out of MIT, out of the groups of Peralt and Sullivan. And so what they've done is they did a ferrite design where they distribute the gapped inductor, the air gap, one air gap per every turn of this pot core inductor. And by doing that, they made it such that the current crowding of the conductors is not as severe, and so you're using more of the wire effectively from a cross-sectional perspective, and so your ESR is not as great. And so this is a good paper, and it was very easy to follow, and they have parametric design results, so you can design your own inductors without having to repeat the FEA. We found that pretty useful, and so this is a good paper to check out. The other thing you need to consider is the common mode current. So you want to put an inductor on both sides of your capacitive coupler. The reason that is if you don't split that impedance up, you can have an imbalance such that you drive a common mode current through ground, and you don't do that as severely if you split your impedance up. So your load is not at a higher potential with respect to ground. So we decided to put both inductors for both legs of the circuit in the same core. There's two ways you could consider doing that: a bifilar winding or individual coils on one core. We went with the individual coil route. The reason that is because we didn't want to deal with the high turn-to-turn voltage disparity, and so with this route you're able to do better turn-to-turn voltage management for your inductor coil, and so we elected to do this route. So here's the design that we did. So we had these individual ferrite pieces, and you could stack these up like laminations. Bits of Kapton tape were used as both shims between all of the ferrite layers to build up the air gap, and also it was pretty convenient. Just it was pretty convenient to use Kapton because it's sticky backed and we could adhere it. And we also used a screen what's it called? A screen printer, not a screen printer.
3D printer?
Not a 3D printer. I'm trying to remember the name of the tool that we used to cut out the Kapton with, but the trick was cutting the Kapton out so it was like stickers, and then we stuck it on the bits of ferrite.
Got it.
And then we 3D printed a little holder for it. So once we stacked it all up, we could just press it into this little holder to hold it together. And then and so this is two inductors with its 3D printed case, and this is the two air core inductors that it replaced. The other thing you don't want to, other reason you don't want to use air core inductors is that the end turns in particular of air core inductors see a lot of eddy current loss because the fringe field cuts through them. And so the ESR of the inductors was reduced by over an ohm just by going from the air core inductors to the ferrite core inductor for two reasons. A, we used less length of wire to achieve our inductance, and B, the fringe field wasn't cutting through the conductors anymore. And so we were able to, so going to a ferrite core was able to both improve our efficiency and reduce our size, even though this is a multi-megahertz system, which is, most people assume like, oh, it's multi-megahertz, a coreless design is probably going to be more efficient because you won't have the core loss. But we found that wasn't true. We found the core design using the approach outlined by Peralt and Sullivan's groups that was the better route.
Okay. And also, will you also talk about the EMI? Did you do any shielding? Later on, will you talk about it?
That's in our future work. And so, yeah, so we'll have to discuss that later. But so overall, with the printed circuit board capacitive design rules, we reduced the loss by 58%. And then using going from air inductor to a ferrite inductor, we reduced another 43%. So overall, we had a 75% reduction of loss of the ESR of the tank from 6.6 ohms down to 1.6 ohms. Power electronics. So all right, so we're at megahertz frequencies. So we want to do class D or class E. And so in this case, this came from a paper I published on a survey of small gap wireless power transfer systems for inductive and capacitive approaches. This was a paper I did with Zhenjian Dai, published in 2015 in JESPI. So in this case, or was it transactions, or was it panels? I can't remember.
No, just P. Yeah, because it's a very highly cited paper. Yeah. Just P.
Yeah. So so in this case, we've got, if you're going to, so we surveyed what you can get out of, at the time, out of silicon and silicon carbide and GaN for IGBTs and FETs and the like. And then we did an analysis that looked at where the limits are for class D, which is a DVDT limit, and then class E had a switch utilization limit. We found that class D is better for higher power and lower frequencies, and somewhere in the hundreds of kilohertz is sort of where these two basic lines cross. And then class E is better at higher frequency. But this crossover point is already moved. It's out of date. So the crossover point for class D is now in the megahertz. And then similarly, in this case, if you look at a cost perspective, where if you look at dollars per watt and then throughput power, the class D is going to give you more power for a lower cost than class E. And so with these two things in mind, we decided to go with a class D. And this was, our circuit. We went with a classic, class D H-bridge, where this is just one phase of it shown. And these are the devices we used, a simple 50% duty ratio. We had 40 nanoseconds dead time, and we were doing soft switching. So the details of that are included in some of our other reference works, but the other thing we decided to do is, well, we have to track this track a resonance, and or at least maintain the phase relationship that we want between the voltage and the current, because we are doing largely zero current switching. And so to do that, we have our GaN inverter we have our rotor, rectifier, and field, and then we have our series resonant tank. And so we measure the current through a current transformer, and then we use the CD4046 integrated circuit to set up a PLL with using a voltage controlled oscillator to then track that phase relationship. And so in this case, we need, so we have our GAN inverter picked out, but one thing that's interesting is we need to do some impedance matching here. So we have our rectifier, but our rotor field is a certain value. So in this case, if our coupling capacitors are 2 amps per megahertz, and excuse me, and our current is going to be 3 amps RMS in the tank. So if we have, let's say, 1.6 or 2 megahertz, somewhere in there, we have a 3 amps in the tank circuit. And our field power is going to be 675 watts, but with 3 amps in the tank circuit times VAC cosine theta, this gives us, and if the power factor is 0.95, that's 227 volts. And that means that our impedance looking into the AC side of the rectifier is 76 ohms. And then if we reflect that 76 ohms from the AC side of the rectifier to the DC side of the rectifier, that's 94 ohms. And the field, though, the field winding is 42 ohms. And so there's this mismatch. So we have to match these impedances. And so on the rectifier, not only do we have a diode bridge, but we're going to put in a little buck converter to then match the high impedance of the capacitive coupling AC system to the lower impedance of the 42 or 40 ohms of the field winding. And that's just done by adding a low side buck switch in this case. So the field winding, though, is only an inductor to about 2 kilohertz, and then it starts turning into a capacitor. So because of the large parasitic winding capacitance. And so what we decided to do is make a buck converter that ran at 1700 hertz, and it needs a 67% duty ratio in order to do the impedance match. So thankfully, our inductance at 1700 hertz is 3.5 henries, and so the current's going to be very smooth no matter what.
And you have to make sure that this impedance matches with the switching frequency impedance, right? That also should be taken care of.
Right.
Because
so
now,
so the impedance over here is going to be, if you reflect the AC impedance onto the DC side, was 90 some ohms, and that's determined by the operating frequency of the resonant tank. And the coupling capacitance, there we go, and the coupling capacitances. And so because we know what that is, we can have a fixed duty ratio of the buck converter, because the resonant tank frequency isn't going to change much, only a fraction of a percent. So,
got it.
And so because it's a fixed system, we can use a fixed duty ratio.
Got it.
So
Yeah,
this is the unpopulated rotor board. So on this side, diode and some capacitors, and then on the other side of the board is the rectifier. So these are the this is the rectifier, and then the rotor DC link capacitors, and then the rotor buck converter. And the gate drive and driver for the buck converter is all self-powered off the DC bus on the rotor. And then after we populated it, we potted it with epoxy. And then this is the whole system. So we have our stationary GAN inverter, we have our resonant tank inductor, we then have our capacitor boards here, and then the rectifier and the electronics, and And so this is the sort of an overview of the whole circuit, the whole system.
Very good.
And then this is what it looks like on the bench. So here's our machine. And this could have been installed on the inside of the machine, but it makes it a real pain to put probes on if it's on the inside of the machine.
Yeah.
So we mounted it on the outside. And then here's our tank inductor, and then here's our inverter, and then here's the PLL and the rest of it. Right now, my current student Marissa is working on taking this proof of concept box and turning it into a 3x5 circuit board card. When I say 3x5, that's 3.5 inches.
Okay.
And so here's some of our waveforms. We have the input to the rectifier and the output in the GAN inverter, and then the sinusoidal tank current. And then here's the buck converter waveforms on the rotor. Obviously, we did this while it was stationary, so we could take some put some probes on it on the rotor board. And then and so we were able to transfer our 675 watts to the field. And DC in to DC out, we did this, so it was 750 watts in, 675 watts out, so 90% efficient DC in to DC out, which is pretty good considering the multiple conversion stages. So the GAN inverter to the resonant tank to the rectifier to the buck converter. And so 90% was pretty good there. And those are the various measured voltages. I don't know if this video is working, but
I don't think I can see it. Are you playing it outside the presentation? Yeah. Try to play it now.
বলো হ্যাঁ বলো
I'll try to play it.
আমারও হচ্ছিল মাঝে কিন্তু আমাকে কেমন একটা মানে আমি ফোন মানে আমি মনে হয়
I doubt it'll. The refresh rate's probably too low for the video to work well. Here, I'm playing it
আমি
now.
মিউট করিনি
Yes, you can see it. Yeah. The right side one, the vertical video. Yeah, you can see it.
And so this is it spinning on our dynamometer. So we were doing we're running this machine as a generator, and then the rotor board spinning there.
So did you do any multi-physics simulation because your any stress analysis because it's moving, right? Did you do any of it?
We did in terms of, and that was the paper I alluded to from ECC 2019 on the mechanical stress.
Got it.
Yeah, so that was we actually experimentally measured the Young's modulus of the boards using sample coupons, and then spun it up to a speed of 25,000 RPM to ensure it didn't burst.
Oh, very good.
So,
and did you use any multi-physics software? Which software did you use? Any software at all?
We used, I believe we used SolidWorks and ANSYS.
Okay, and that is where those figures are also, right? The ones you showed earlier. 3D.
So we used Maxwell for the electrostatics, and then we used SolidWorks this on structural.
Good, very good. Yeah.
So for the testing as a generator, we just connected the machine to a delta resistive load bank, and as you can see here, we were able to achieve line-to-line voltages, and you can see with respect to the CPC current, the RF tank current, we were able to push the machine into saturation and line-to-line voltage, and we were effectively exciting the machine. And you can see here that we were hitting the rated power, and then at the 30 kilowatt continuous rated power point, the voltages and currents of the machine look good. And at the base speed, we hit the rated power, and we were happy with the performance of the machine.
Good. Very
So we
smooth.
didn't talk about, or I didn't present much on the controls. So for controls, you can do burst mode control, and so how you do burst mode control is discussed for capacitive power transfer is discussed in the publication down there with my students JJ and Skylar, and that's in JESP. And then one of the other existing opportunities that we're working on now is using this system to also be the resolver of the machine. So you need an encoder or resolver for doing field-oriented control. And one of the neat things is that, so the PLL, if you look at the error signal in the PLL, which tracks the resonant frequency, the error signal correlates to the position of the rotor, because the resonant, the discs, while they're very flat, they're not perfect. And so the resonant frequency will change a fraction of a percent as the discs rotates, and so the PLL tracks that. And so you can use the PLL error signal to tell you where the rotor is. And so you could enhance this error signal by purposely introducing a little bit more saliency into the capacitive discs. And when you do that, you could use that signal to serve as the encoder resolver signal in your field-oriented control scheme. Another thing you could do is use the ripple in the rotor field winding introduced by the buck converter switching. It introduced a little bit of ripple in the rotor field winding, and that ripple will show up in the back EMF of the main stator windings, and that's spatially dependent. Here's us taking a video of where we're moving the shaft by hand, and you can see the ripple on the rotor show up in the main field winding, and as you spin the shaft by hand, that ripple shows up in the different axes according to the location of the rotor. And so you can do both a saliency tracking or a injection signal tracking method with this capacitively coupled technique.
Good.
And then, so approaches going forward for what I'm working on, we've got, right now, our group is working on transitioning from being in the low megahertz into the ISM band, which is in the 6.78 or 13.56 megahertz GaN inverter frequencies. So it's really fast. We're also transitioning from doing something for like a 30 kilowatt machine to a 150 kilowatt machine. So this is going to need 30 or around 30. Around 3 kilowatts of field power. And so we're transitioning our power electronics to be from a couple megahertz to more than 10 megahertz, and from around 1 horsepower to around 5 horsepower. And then, so that's my presentation. That's what I had planned for today. I'm ready to field any questions you may have.
Just before, and what sort of PLL did you use? What's like SRF?
This was the PLL was an analog chip. It was the CD4046 chip.
Got it.
A few dollars on DigiKey or Mauser.
Yeah, thank you very much, Prof. We'll take some few quick questions before we wrap up. Please unmute yourself and go ahead. Please go right ahead with the questions.
Hi, Dan. How are you? This is Eric's friend, Kaushik. Remember me?
Hold on. I'm trying to get my screen back so I can see people. Hold on.
Yeah. This is Professor Kaushik. Yeah. Go ahead, Prof.
Trying to. Right now, I can only see my own screen for a second. I just need to.
Okay.
Fix this.
Yeah. I think now you can see. Can you see now?
No, not quite. There we go. Okay. Hey, Dasha.
Hey, how are you, man?
I'm doing well.
Good, good. Nice presentation. Thank you.
Thank you.
Yeah.
Yeah, I wish I would be seeing you in ECC this year, but
Yeah, but
we're all
not happening. Not happening. Yeah. Yeah. So, a few quick questions. See, one is that I didn't understand this amps per hertz. You said it is like this. That yeah, I think that's like how. Once.
Yeah, I don't know if
Yeah.
any of my screen is still shared or not. I don't think.
Yes.
Yeah, we can see it. We can see it.
Good.
Yeah.
All right. Let me get to it here.
Others, please post your questions in the chat.
All right. Okay. So let me move this over.
So, see, what is you have is that you know what is the load resistance that you need to supply, and you know at what voltage, right? That's your 650 watt, and I think it is 45 ohm or something, right? That comes from the specification, right?
Yep.
And then the rest is the design based on that, right?
Correct. Yeah.
Right.
So
the first question will be that how you know what should be your capacitance, right?
So that's
Or
so the capacitance.
Dan, maybe you can go to the slide.
What was that?
Can you just go to the slide so that others also
Let me
know?
go to the. One second here.
Okay.
And can you see it?
We can see
You
the
see
questions.
I don't know if you can see the slide right now. You see the slide?
Yeah, we can see only the question slide.
but
Oh, okay, so I'm on a different slide at the moment, so hold on a second.
Okay.
so there is a lag.
Let me know if you can see. I'm on the slide that's
Right. We can see it. Yes.
okay. So in this case, so there's a couple constraints. So this amps per megahertz refers to the maximum current that a coupling capacitor can support before the electric field exceeds a value where you'd have an arc, and so that's determined by these lines.
Right.
And when we get to here, so this field, so you have I out and V out, and if that's your field winding resistance,
Right.
The impedance of this is such that it is lower than the impedance of this circuit, VAC and IAC. So in this case, we were putting 3 amps through here, and then with a higher voltage, VAC, and then we had to, once we rectified VAC, we then had to bucket because we weren't able to push the value of the current needed directly from the rectifier. So this system required a higher impedance to accommodate the amps per megahertz limitation of IAC.
Okay.
And so we had to bucket down after we rectified it so we could transfer the power using a higher voltage and less current.
So that means that for the given frequency, right? So you have that limit on the electric field, and then you have decided, okay, I'm going to do it at 1.5 megahertz, right? Right. And then you know that with this, and your area is also sort of known, that A in your equation. So then what you want to do, you want to push the maximum current that you can, given these limitations, right? So that's how the 3 ampere is coming.
Yep.
Okay.
Correct.
So what does this mean that if if I do this design with 1 ampere, right? Given this, what does this mean? It will mean a lower transfer efficiency or a bigger size of the
So
system.
what that so if you do the transfer with 1 ampere instead of 3, that means you do a couple different things. You could either have a higher DC bus. Oops, oh, it moved on me. You could either have a higher DC bus on your GAN inverter and then use more voltage but at a lower current on the AC side. You could also, if you use 1 amp, unless you increase the voltage, you're not going to be able to transfer as much power.
Okay, I understand. So the thing is that this fundamental of the square wave is given based on the DC bus.
Yes.
Right?
Yes.
So
Yeah.
and now the power is given, so the
Yes.
current is given from there. Oh,
Yep.
okay, I see. Because you are operating at resonance, right?
Yeah. So for instance, like the L and the C cancel
got
at
it now.
resonance,
Okay.
so VAC appears
Okay.
across,
Okay.
or at least the
Got it.
fundamental.
Okay. Awesome,
But-
man. Okay, understood. See,
Yeah.
now a few very quick questions.
Yeah.
One is that what about you are applying a square wave, right? And I can understand that you are doing frequency tracking and operating at resonance, right? But what about the other harmonics? Because that depends upon the Q, how
Yeah.
well they are filtered out, right?
Yeah. So in this case, so this this tank has a very it's relatively steep in that the characteristic impedance of the tank is very high, square root of L over C. Oh, where is it? And so gotta get to waveforms. Hold on. Yeah, here we go. So in this case, the reason the 2 volt, the 2 square waves that you see, the solid black is the output of the inverter. Dashed black square wave is the AC terminal input to the rectifier.
Okay.
The reason that's a square wave is because it's got a stiff voltage on the other side of it. There's a DC link, and then the tank current is almost purely sinusoidal. We couldn't measure the harmonics on the tank current.
Yeah.
That's because the characteristic impedance of that series tank is so high that the other harmonics just don't make it through.
Okay. Now the last quick question. So the thing is that looks like that you are doing GCS, right? You are because your current and voltage is in phase. So
yeah, they're largely in phase. That's not perfect. The reason, we found the optimum condition for us was so at input to the rectifier, the capacitance of the diodes shows up on there, and so what happens is we operate the system on the GAN side slightly on the inverter side slightly inductive, such that the inductive bars of, even though we're on resonance, well, we're nearly on resonance, we're operating slightly past it, and that's because we're trying to get power factor to balance because of the parasitic capacitance on the diodes on the input to the rectifier, and so you can see that the zero crossings of the current fall directly in between the zero crossings of the rectifier input and the inverter output, and that's so we do a little bit of power factor balance there, and we found that was our optimal, or not optimal. We found we had our best efficiency when we balanced the two, rather than placing the sine wave to be purely in line with the inverter or the rectifier. Splitting the difference gave us the best result.
So I was asking about that GCS, right? So if you do GCS, like you see, sometimes for fetch people prefer GVS than GCS because in GCS you have that COSS dump, right? Like when the switch turns off, the charged output capacitance will discharge in the channel, right, leading to a loss. So that's why I was just wondering that do you prefer? You seem like you prefer GCS over GVS, but GVS again depends upon current and all that.
Yeah, I mean this is something that we're still trying to debate on what to do next with it, because this system is very much sort of a proof of concept, and we're trying to decide when we scale up to a higher frequency, when this matters even more, what the best solution is. And so, yeah, if you want to chat more about it, maybe offline.
Yeah, we can do that, man. Very interesting. Yeah.
So,
all right, thanks.
Yeah. Before Professor Kaushik logs off, Dan, can you talk about C-Motive a little bit?
Oh yeah, I'm sorry, I've been ignoring the chat window.
No. You can just talk about C-Motive.
Yeah.
People, just a little bit.
Yeah, so I have a startup company called C-Motive Technologies that after I left graduate school, I founded with some colleagues, and it's a motor.
I got it.
Hello, little one. I have 3 little ones myself. They're 5, 3, and 1.
Yeah, go ahead then.
But anyway, in C-Motive though, what we work on is electrostatic motors. So these are motors that don't use steel, copper, magnetism of any kind. So they use electrostatic forces. So one of the defining parts of my career so far is I've devoted a large chunk of my time to capacitively coupled systems. And these capacitively coupled systems are using electric fields to do work. And so C-Motive is dedicated to making electric field-based machinery instead of magnetic field-based machinery. Currently now we have 9 employees, and
very good. Expanded over the years.
And so when we've built up, we've raised venture capital funds, government, federal grants.
Very good.
It's always a challenge, and so this past year we got our first contract for a customer contract.
Congratulations.
So now we're trying to deliver our very first product within the year, and so it's
very good news.
It's exciting and challenging.
Yeah. Definitely, but very good. Yeah, I think you have been looking after that startup for quite a number of years. Very good to hear.
The startup was founded in 2012.
Whoa.
It's been going for 8 years. It's been what I call a slow burn. And the reason that is because hardware is way more difficult than making an app.
Yeah. Totally agreed.
As power engineers, I don't mind saying that what we do, because it's both theoretical and physical, commercial, is therefore is way harder than a software system.
Yes.
My computer engineering colleagues would get very mad at me for saying that, but I think it's the truth. Yeah. Even with EV startups, it takes like at least 2 years to bring out a product or make some new changes. It's the timeline is very long, but good, very good. Yeah. So before I think we will wrap up, I think is there a question? What are the problems that did you face any problems in tuning PLL, or did you use just that IC? So I find that oftentimes basic control techniques work well if you adhere to good design practice. So in this case with the PLL, we didn't have too much issue because if you look at the quality of the sine wave, it's very sinusoidal. So and that has to do with the high characteristic impedance of that tank circuit. It yields a very high quality current sine wave, and so the zero crossing detection on that sine wave was very clean.
Good. Yeah, I think we are already over time. I had just one quick question about GAN. Did you face any false turn-on issues when you use GAN? Because
Yes,
the layout is
the thing that I've found is that we've spent more time just trying to prevent shoot-through issues with GAN, particularly managing the common mode capacitance and the isolated gate drives. Also, the parasitic capacitances for DVDT events and things like this. And so we had to go through several board revisions of trying to get the layout right to prevent these occurrences. And so if anyone wants to do a cool research topic, if someone can come up with a definitive way of creating a design structure for high frequency, high DVDT layout for GAN that is, right now it's more sort of base, good design practice rules and trial and error. But if someone comes up with the definitive way of doing it right the first time, I think that would make someone quite famous. So for the students in the room, get to work on it.
Yeah, EPC has one. They released one video recently for layout basics, but I don't know to what depth they cover. But EPC, Alex Lidow's startup, they have a layout video release based on layout. Yeah, because that's why I asked this. So, just think about that because GAN was my question. Yeah, go ahead, Prof. Go ahead.
Quick question, Dan. It was you use GAN systems, right?
Yeah, I use their hardware. Yeah.
The 650 volt device, I think.
Correct. Yep.
Right. Thanks.
Yep. So we use their parts. So they've worked well for us so far. The challenge that we found is managing the parasitic capacitances and the board layout, and then and then sometimes, at least for student built hardware, sometimes it can be difficult to cool because of compared to more traditional packaged devices. So if anyone has good references on this stuff, I would be they're willing to send me. I'm always willing to learn.
So just one quick question: did you use GAN only for the footprint or just for the megahertz switching capability?
We just used GAN for the megahertz stuff, and then for the main traction inverter, used traditional IGBTs.
Dan, because
say something there.
Sorry.
Go ahead.
So because you said, so are you using a top cool device or it was a bottom cool?
These have been
through
bottom.
PCB you did.
These are bottom cooled, but we're moving to a top cooled.
Okay, I see. Okay,
yeah,
cool.
So for the higher power stuff, we're moving to a top cooled device. And Karama Freedy's group at Cornell has had some success, I know, with 13.56 megahertz work using top cooled devices.
Yeah. Thank you very much, Prof. Yeah, I think we can wrap up. We're already over 1 hour. Thank you very much for such an very interesting presentation.
Thank you very much, Dan.
Thank you. Thank you for hosting me. I had a good time.
Yeah.
we'll have to find another venue to catch up.
Yes.
Yeah,
Yes.
Professor Kaushik is the Pell's chair in Bangalore. Pell's.
Yeah. So
Yeah, Dan-
Janmaja arranges a.
Yeah.
Sir, you said
Dan is
something?
the Dan is the chair in Madison, right, Dan?
I was last year. Now I'm vice chair in Madison
See.
for IAS PES. I don't know. We currently don't have a Pell's chapter in Madison.
Good.
So
All
we'll have to
right.
work. All right.
Yeah.
Take care, everyone.
All
Yeah,
right.
thank
Thank
you.
you very much.
Thank you.
And let's
Bye-bye.
hope to meet again sometime. Yeah.
Yes, indeed.
Yeah.
Take care.
Yes. Bye bye. Take care. Bye
Thank
bye.
you, everyone. Thank you for joining in. Thank you, Prof. Yeah. We'll end it. Yeah.